Hello my dear students, today I am going to start the third unit, which is electronic spectroscopy. This is the first lecture of this unit. In this unit we are going to discuss about the selection rules for electronic transition, the spectrum of hydrogen atom, the fine structure of spectrum of the hydrogen atom. In addition to this, we'll discuss the spectrum of hydrogen-like atoms such as lithium atom, the Born-Oppenheimer approximation, and also the FRANK-CONDON principle. First of all, we will start with the selection rules for electronic spectra. The selection rules for electronic spectra are quite complicated, and in general, the three rules are used. However, these rules are not always strictly followed. These are firstly the electronic transition in which the spin of the two states are the same are allowed. For that means delta S is equal to 0, which means that transition between singlet to singlet or doublet to doublet or triplet to triplet is allowed, but not from singlet to triplet or doublet to triplet. Secondly, the transition between symmetric and antisymmetric states are allowed. That is, for homonuclear diatomic molecules, the transition Z to unZ or unZ to Z are allowed, but not Z to Z or unZ to unZ. Thirdly, the transition in which the change in the component of orbital angular momentum along the internuclear axis are allowed. That is, delta lambda is equal to 0 or plus minus 1. So which means that the transition between S to S or S to P is allowed, but not S to D. Okay. So applying these selection rules, we will discuss the electronic spectrum of hydrogen and hydrogen-like atoms. So let us start with the discussion of the electronic spectra of hydrogen atom. In hydrogen atom, due to the absence of the inter-electronic effects, all orbitals with same n value have the same energy. Therefore, 2s and 2p orbitals, for example, are degenerate, as are the 3s, 3p and 3d. However, the energies of 2s, 3s and 4s orbitals are differ considerably. For s orbital, we have psi ns is equal to r by n naught exponential minus r by n into n naught. Give it equation number 1. From the Schrodinger equation, we have En is equal to minus m e to the power 4 8 is h square epsilon naught square n square, this much joule. Give it equation number 2. Now if we convert this energy in joule into centimeter inverse, then we can write epsilon n is equal to minus m e to the power 4 divided by 8 h cube c epsilon naught square n square, which is equal to minus r by n square centimeter inverse, where n is equal to 1, 2, 3 and so on. Give it equation number 3. Here epsilon naught is the vacuum permittivity and r is called the Rydberg constant. Since p, d orbitals have same energies as the corresponding s orbital, so equation 3 represents all the electronic energy levels of this atom. Now the lowest value of epsilon n is equal to minus r centimeter inverse when n is equal to 1, and this represents the most stable state, which is the ground state. Epsilon n increases with increasing n and reaching a limit of epsilon n is equal to 0 for n is equal to infinity. This represents the complete removal of the electron from the nuclei, that is the state of ionization. The energy levels for n is equal to 1 to n is equal to 5 and L is equal to 0, 1 and 2 only are sketched in this figure. So here you can see that the energies of the 2s and 2p orbitals are same, That means these are degenerate. Similarly 3s 3p 3d or 4s 4p 4d or 5s 5p and 5d are also degenerate. That means their energies are same. Okay, so this figure represents some of the lowest electronic energy levels of the hydrogen atom. In order to discuss the spectrum, we follow the selection rules. Delta n is equal to anything and delta L is equal to plus minus 1 only. Therefore, we will find that an electron in the ground state, say 1s state, can undergo a transition into any of the p state. Okay, that means 1s to np, where n is greater or than equal to 2, is allowed, while a 2p electron can have transition either into an s or a d state. That means 2p, the transition 2p to ns or nd is allowed. Since s and d orbitals are degenerate, the energies of both these transitions will be identical. The transition 1s to np means that the electron from the 1s state can undergo transition into 2p, 3p, 4p or 5p and so on. Similarly, the transition 2p to ns or nd means that the electron from the 2p state can undergo transition into 3s, 4s or 5s, or from 2p state it can undergo transition into 3d, 4d or 5d as shown here. So this figure represents some of the lowest electronic energy levels and transition between them from the single electron of the hydrogen atom. In general, an electron in a lower state, say N1, can undergo a transition into higher state, say N2, with absorption of energy delta epsilon is equal to epsilon N2 minus epsilon N1 centimeter inverse. So nu bar spectra is equal to minus r by N2 square minus within bracket minus r by N1 square, which is equal to r into 1 by n1 square minus 1 by n2 square centimeter inverse. An ideal spectral line will be produced in emission if the electron falls from the state n2 to n1, and in both cases L must be unity. So let us consider the transition 1s to n2p, where n2 is equal to 2, 3, 4 and so on. For these transitions we get Lyman series. Therefore we can write nu bar Lyman is equal to r into 1 by 1 minus 1 by n2 square, okay, which is equal to r minus r by n2 square in centimeter inverse. Now when we substitute n2 is equal to 2, 3, 4, 5 and so on, we will get the value of nu bar Lyman is equal to 3r by 4, 8r by 9, 15r by 16, 24r by 15 and so on centimeter inverse when n2 is equal to 2, 3, 4, 5 and so on. Now when n2 is equal to infinity, we have nu bar Lyman is equal to r centimeter inverse, which represents the complete removal of the electron. The appearance of this Lyman series spectrum is shown below. Here you can clearly see the different lines in the Lyman series. This one is the first line in the Lyman series, this one is the second line in the Lyman series, this one is the third line in the Lyman series and so on. So from this spectrum it is found that the value of R is equal to 109677.581 centimeter inverse, which is obtained from this spectrum only. Now we know that 1 centimeter inverse is equal to 1.987 into 10 to the power minus 23 joule. So if we convert this value from centimeter inverse into joule, then we will have the precise value of the ionization potential from the ground state, which is equal to 2.1781 into 10 to the power minus 18 joule, or approximately 13.595 electron volt. So this is the ionization energy of the hydrogen atom. That means this much energy must be supplied to the electron for complete removal of the electron from the nucleus. Okay. So this figure represents the Grottorian diagram for the spectrum of atomic hydrogen. Here you can see the different lines of the hydrogen spectra. This is the Lyman. These two represents the Balmer. This one is percent, and so on. Okay. So here the Lyman series of lines are obtained when the electron falls from the NP state to the NS state. Similarly, Balmer series of lines are obtained when the electron falls from NP to 2s or NS or ND to the 2s state. In the same way, we can explain also the same for the percent, bracket and Pfund series of lines. Okay. This is the fine structure of the hydrogen atom spectra. Here the splitting of energy levels and the essential details of the energy levels of the hydrogen atom are shown. So to discuss this, first of all, let us see the terms arises from the different energy levels. So we know that the terms symbols is represented by 2s plus 1 Lj, where S is the spin and J is the microstate, which is equal to L plus S up to L minus S. So the value of a small l is equal to 0, 1, 2, 3, which represents the orbitals S, P, D, F, etc. So the value of capital L for hydrogen atom is also is equal to 0, 1, 2, 3, since there is only one electron in hydrogen atom. So the terms will be S, P, and D only. Okay. So since hydrogen has one electron, so S is equal to half. So therefore 2s plus 1 is equal to 2 into half plus 1 is equal to 2. So all the terms will be doublet. So when S, in case of S orbital, L is equal to 0, so it represents a S term. So therefore this is the 2s state. So similarly, when L is equal to 1, it represents a P term. So the term will be 2p, this one. And when L is equal to 2, the term will be D, since the spin is multiplicity 2s plus 1 is equal to 2. So the these energy levels, D levels, are represented by the term 2d. So when since the value of S is equal to half, so the value and L is equal to 0 for the S orbitals. So therefore the value of J is equal to half plus 0 up to half minus 0, which is equal to half. So therefore the S orbitals are not splitted. So it has only one state, having the microstate value half. For the 2p state, the value of L is equal to 1 and S is equal to half. So therefore the values of J are 1 plus half up to 1 minus half, which is equal to 1 plus half is equal to 3 by 2 and 1 minus half is equal to half. Likewise, for the 2d term, the value of L is equal to 2 and value of S is equal to half. So therefore the value of J will be 2 plus half up to 2 minus half. So that means 2 plus half is equal to 5 by 2 and 2 minus half is equal to 3 by 2. Okay. Therefore the 2p and the P and D levels will be splitted into 2 microstate as shown here. So applying the selection rules, delta n is equal to anything and delta L is equal to plus minus 1 only. Along with this, we have another selection rule, delta J is equal to 0 plus minus 1. We can have these transitions which are allowed. The transitions will be the same as those we have discussed in case of the atomic spectrum of the hydrogen atom. but here the difference is that you have to consider the microstates also. So remember that since the as per the selection rule, delta J is equal to 0 plus minus 1, that transition from the state half to half is allowed and half to 3/2 is allowed, but the transition half to 5/2 is not allowed, because in case of the transition from half to 5/2, the delta J value will be 2, okay, which is not allowed. Now let us discuss the electronic spectrum of lithium atom. So lithium, sodium, potassium, rubidium and cesium etc. all have single electron outside a closed core shell. Therefore they resemble hydrogen, and this resemblance is augmented by the fact that we can ignore the angular momentum of the core and deal merely with the spin and the orbital momentum of the outer electron. The energy level of the lithium are shown here. You can see the figure represents some of the lowest energy levels of lithium atom along with some allowed transitions. Here the 1s state is filled with electrons which do not take part in spectroscopic transitions, as it requires much less energy to induce the 2s electron to undergo a transition. So therefore the 1s state is omitted. So here also the selection rules are delta n is equal to anything, delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. So accordingly the allowed transitions are will be 2s half to np half or np 3/2. As is seen here, the different transitions are which are allowed are shown here in this figure. Okay, now next we are going to discuss two important principles which are applied to discuss the electronic spectrum. The first one is the Born-Oppenheimer approximation and second one is the FRANK-CONDON principle. So first of all, let us see what is the Born-Oppenheimer approximation. The theory of electronic as well as molecular spectra had been made quite easy by this Born-Oppenheimer approximation, which is explained as the nuclei of the atoms are much some 1000 times heavier than the electrons. Consequently, the electrons move so much rapidly in comparison to the sluggish nuclei that they travel the available space many times in the period the nuclei change their position only slightly. Considering this, in 1927, Max Born and J. Robert Oppenheimer suggested that if it was a good approximation to treat that the motion of the nuclei and the electrons are independent of one another. According to this Born-Oppenheimer approximation, the electronic energy may be treated separately from the internal energies of the nuclei. That is, the energies of energy of a molecule may be considered as the sum of the electronic, vibrational, rotational and translational energies. So therefore mathematically we can write E is equal to E EL plus E VB plus E ROT plus E 3R, where all these terms represents the electronic, vibrational, rotational and translational energy. So now we can neglect the translational energy since it is not quantized. So therefore we can write E is equal to E EL plus E VIB plus E ROT. So therefore the energy change for an electronic transition is given by delta E is equal to E dash minus E double dash, which is equal to E dash EL minus E double dash EL plus E dash VIB minus E double dash VIB plus E dash rotational minus E double dash rotational, which can be written as delta E is equal to delta E EL plus delta E VIB plus delta E ROT. The frequency of the electronic transition is given by the Born-Oppenheimer condition, which is equal to nu bar is equal to delta E by Hc, which can be written as nu bar is equal to delta EL plus delta VIB plus delta EROT divided by AC centimeter inverse. So this equation shows that how an electronic transition possesses the vibrational and rotational fine structure. Next is the FRANK-CONDON principle. A very useful principle for investigating the vibrational structure of electronic spectrum is provided by the FRANK-CONDON principle. This principle states that an electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance appreciably during the transition. To demonstrate the FRANK-CONDON principle, an electronic transition is represented by a vertical line as shown on the plot of the potential energy versus the internuclear distance in this figure. Here E0 is the ground electronic state energy and E1 is the first excited electronic state. The minimum in the potential energy curve for the excited state occurs slightly greater internuclear distance, since the bonding in the excited state is weaker than on the ground state. So thus when a photon falls on the molecule, the most probable electronic transition according to the FRANK-CONDON principle takes from V double dash is equal to 0 to V dash is equal to 2. That means the transition 0 to 2. So transitions to the other vibrational levels of the excited state occur with lower probabilities, so that their relative intensities are smaller than the intensity of the transition 0 to 2. So as you can see here in this figure, that when the molecule undergo transition from the state 0 to 2, there is no change in the internuclear distance. That means the internuclear distance does not changes as when the molecule undergo in electronic transition. Okay. We can consider another case of diatomic molecule which has a potential energy curve E0 in the ground state and two potential energy curves E1 and E2 in the excited state as shown in this figure. So this figure represents the potential energy curve for the ground state and two excited states of a diatomic molecule. In this figure, the transition indicated by arrow A, small a, has the maximum intensity according to the FRANK-CONDON principle. The transition B1 ends in the lowest vibrational level of the first excited state, where the molecule is still held firmly. But the transition B2 promotes the molecule to a point where the change is far above the potential energy plateau of state E1 at large distance, with the result that the molecule dissociates. At an internuclear distance corresponding to the point C, the molecule may undergo a crossover from one state to another without energy change and continue to dissociate. So I am giving you a homework. The question is state and explain FRANK-CONDON principle. Discuss how this principle is appreciable to explain the intensity distribution of vibrational bands in electronic transition. So if I have tried to make you understand about the two figures in the previous slide, where we have already discussed about the intensities. So you carefully listen to my explanation and try to answer this question. I hope you can easily write the answer by listening the discussion. So that's all I have to discuss in today's class. I hope you have understand and I am able to make you understand. So you read the different books and try to prepare your notes. If you have any doubts or any problem, then feel free to contact me. So let us stop here. See you in next week. Till then, enjoy your learning.